thank you very much for getting this opportunity to present. So this is work performed by many persons, and I've listed all of the most important contributors here on this first slide here. So today I, Pontus, and Jennifer Bahr from IVL will present the work within ABC-iCAP on the socio-economic analysis of a sustainable investment scenario targeting both air pollutants and climate forces in the Arctic Council nations, with a special focus on black carbon and methane emission reductions in the years 2020 to 2050. So this first slide just illustrates the overview of the methods used in our work. And first, the most important is of course the emission scenarios, which we based on the EASA gains model, and I will talk more about that soon. And I will give a general overview of the background to the socioeconomic analysis, so how to assess the climate impact and the health impact of air pollutants and climate forces from the Arctic Council nations. And then Jenny will talk more about the actual socioeconomic analysis, both considering climate change and health effects of air pollutants. So first about the emission scenarios. This work is based heavily on the already existing emission scenarios developed with the EASA gains model, and the emission scenarios were used in the latest AMAP assessment report on short-lived climate forces from 2021. And basically, these emission scenarios are built on the energy production scenarios from the World Energy Outlook 2018 report. And those energy production scenarios covers two different scenarios. The first, a new policy scenario, where the global emission pathways of greenhouse gases are comparable to the SSP2 4.5 emission scenario, which was used in the latest IPCC assessment report from 2021. And then we have a more of a sustainable development scenario, which result in rapid phase out of fossil fuels. And these CO2 emission pathways in this energy scenario is more comparable to the SSP1 2.6 emission scenario used in the latest IPCC assessment report. And this figure here with the CO2 emissions illustrate the pathway of the CO2 emissions using these two different energy production scenarios. So the new policy scenario, where you have relatively minor CO2 emissions until 2050, and there's the STS scenario where you have substantial CO2 emission reductions. And apart from the energy production scenarios, we also use two different air pollution and short-lived climate force or emission control strategy scenarios from the gains model. The first is called the current legislation emission scenario, where the current air pollution legislation is implemented as of the year 2018. So that is a less ambitious air pollution emission scenario. And then we have a second, more ambitious scenario where you have the maximum technical feasible reduction scenario, where you use all the best available technology for emission reductions on air pollutant and methane. So in combination, we consider three different emission scenarios, one combining the new policy scenario on energy production with the current legislation air pollution emission scenario, a second with a new policy scenario on energy production, together with the maximum feasible reduction in air pollutants. And the third scenario, which is the most ambitious, is the sustainable development scenario for phasing out of fossil fuels, together with a maximum technical feasible reduction scenario on the air pollutants. So this slide then illustrates the estimated black carbon and methane emissions from the GAINS model. And here to the left here shows the black carbon emissions in kilotons per year, according to the current legislation emission scenario in 2020. And then the current emission legislation scenario from 2050, and then the maximum feasible reduction scenario and the maximum feasible reduction and sustainable development emission scenario for 2050. And here you clearly see that there is great potential in reducing black carbon emissions by applying this kind of more end of pipe maximum feasible reduction emission strategies. But you gain additional reduction in black carbon if you also phase out the fossil fuels. And I also wanted to just compare these anthropogenic emission sources from the GAINS model with estimated wildfire black carbon emissions from the latest global fire emission database. This is just to average the black bar here from the wildfire emissions in average in 2015 to 2020. So they are comparable to the total anthropogenic emissions in the present day. Similar to the right here, you showed is that the methane emissions from the major sectors emit, also the main sectors emitting methane from anthropogenic sources is the fuel production and distribution, and followed by agriculture and waste. So then a little bit about the climate impact of black carbon and how we assess that in our work. We base our work on a recent study by Räisänen et al., which used the Norwegian Earth System model NOR-ESM to study how black carbon radiative forcing and global surface temperatures are impacted by where the emissions occur and what season it is. And based on their model result, they developed a Fortran-based tool to facilitate further use of the results. And this tool we have used to generate the results we need for our socioeconomic analysis. And this bar chart here shows the estimated global surface temperature response per unit black carbon emissions in millikelvin per kiloton. And we separate it based on what where the emissions occur in what Arctic Council nation and also what sector it is emitted from. So I want to highlight here that especially the flaring, Russian flaring has a substantially larger climate impact per kiloton of BC emitted compared to many other sources. And this is due to, again, what has been mentioned before, mainly the black carbon deposition on snow and ice. And also want to highlight that Arctic international shipping here at high latitudes also have a very large temperature response per kilogram of BC emissions. And this bar chart then summarizes the estimated total surface temperature response due to black carbon emissions in different Arctic Council nations. And you clearly see here that the contribution from Russian emissions are substantially larger than any other Arctic nation. And this also now includes estimate on wildfires, and that is from the average from 2015 to 2020. And the Russian impact is larger, not only because of the magnitude of the emissions, but also because they are the temperature response per kilogram of black carbon is generally greater from these high latitude sources. I also want to highlight this, which have been presented in earlier presentation, for instance, by Russell, that in 2023, the total BC emission in boreal forest region were about 4 times higher than the average from year 2015 to 2020, according to the Global Fire Emission Database. And this is mainly due to the enormous fires in Canada. And we try to estimate that using this Fortran-based tool from the Räisänen et al. Study. And based on this, we estimate that the average spring to summer and autumn global surface temperature increase only due to the black carbon emissions from the boreal wildfires contributed to a net global surface temperature increase of 0.15 degree Kelvin or Celsius. So based on this Earth system modeling paper, we have also tried to estimate the global temperature potentials of black carbon on different on 20 and 100-year perspective. And we compare this against existing data from regional global temperature potentials of black carbon. And I want to highlight here first that for our estimated global temperature potentials in our project for the Nordic countries are only looking at the black carbon in the air are comparable to previous work by Lund et al. 2020. They only assessed it for average for Europe, while our global temperature potential estimates for US is a bit lower than the values in Lund et al. For Russia, on the other hand, our values are a bit higher. And then I also especially want to highlight the global temperature potentials for the Alaska, Russia, and Canada, and also international shipping that is substantially larger than for any other region. And then we also have to talk about a little bit about other climate forces, and we have used global temperature potential data from this recent paper by Marianne Lund et al. And in this study, I especially want to highlight that they have more negative global temperature potentials, especially for NOx emissions compared to previous studies. And this is because this recent study by Lund et al., they also take into account how NOx contribute to nitrate aerosol production and how this nitrate aerosol cooled the climate on Earth. So based on these global temperature potentials from all climate forces, we estimate the net total CO2 equivalent emissions from the different Arctic Council nations. And this figure illustrates this. So here you have global temperature potential on a 20-year perspective calculated CO2 equivalent emissions for United States, Russia, Canada, and the Nordic countries. And it's separated based on the different climate forces here. And this is for the maximum feasible reduction and sustainable development scenario. And here you clearly see that you can reduce the CO2 equivalent emissions substantially using this emission scenario, and about the total reductions until 2050 could be at least 50%, and about half of that reduction could be a result of mitigating methane emissions. And then to summarize the climate impact calculations, so compared to the current legislation, emission scenario, the maximum feasible reduction and sustainable development scenario could result in a 54% lower anthropogenic CO2 equivalent emissions in 2050 if we use the global temperature potential 20-year emission metric. Methane emission reduction policies can significantly reduce the climate impact from Arctic nations during the next few decades. Approximately 24% of the lowered CO2 equivalent emissions could be attributed to methane reductions. BC from anthropogenic sources, including wildfires in the Arctic Council nations, have a significant impact on the global surface temperature on Earth. However, when we look at this global temperature potential on a 20-year or more perspective, the reduction policies on black carbon appear relatively minor on a long-term perspective. And then considering the increasing wildfire emissions in the Arctic Council countries, we need to take this into account in the future socioeconomic assessments. However, this is outside the scope of this present work. Then I will finally show two slides on the air quality assessment and the health impact in our work. This we base entirely on the GAINS model, which use emission scenarios which are calculated based on atmospheric transfer coefficients derived from the global chemistry transport model EMAP. And the upper plot here shows the absolute PM2.5 concentrations according to the current legislation emission scenario in year 2030. And the lower plot shows the relative PM2.5 concentration change between the current legislation and the maximum technical feasible reduction and societal development scenario in year 2050. So here you clearly see that you have substantial reduction in PM2.5 in North America, especially in US, and also in Eastern Europe and Russia. And using these data, we then assess the health impact, or primarily the number of premature deaths in the Arctic Council countries. And this is done in GAINS by population exposure, which is calculated by overlaying the ambient PM2.5 maps with projected population data. And the air pollution mortality is assessed using integrated exposure response functions from the World Health Organization. And in total, the number of saved life, comparing the current legislation, emission scenario, and the maximum feasible reduction scenarios, amount to about 80 to 90,000 people per year in total in the Arctic Council countries. And the most lives saved you find in Russia and US, largely based on the number of the large population in these countries, but also the levels of air pollutants. So with that, I leave the word to Jenny.
Yes. Thank you, Pontus, and thank you all for inviting me. I will take over here with the socioeconomic parts of the study. Some more words about the methodology. We have used an updated value for a statistical life from a recent meta study. We have also used an updated value for one carbon dioxide equivalent from a recent study published in Nature. For emission controls, we have used data from the GAINS model and average values of mitigation cost calculated from IEA data. So we have focused on the largest direct costs and benefits. And our study does neither include indirect costs on the economy caused by investments nor health effects that doesn't cause death but lower quality of life or loss of work participation. We have used year 2020 as a base year and use a 2% discount rate. Next slide, please. So here are our preliminary results. As you can see, the largest socioeconomic effect is the net climate benefit. It consists of different costs: temperature, mortality, effects on agriculture, sea level rise, and energy cost for residential and commercial buildings. The second largest effect is investment in the best available technology for both reduction of air emissions and climate forces. The last post is prevented mortality benefits. It's the benefits from a reduction in mortality due to PM2.5. The total results is rather large welfare benefits for the society. Next slide, please. So, but different actors are affected differently. So this figure aims to show how different effects affects different groups of people and actors. The people that benefit from limited climate change isn't always the same that benefits from reduced pollutions. And those people that suffer those consequences aren't the same as the actors that are supposed to pay for the cleaner technology. All in all, this means that those investments won't be done automatically. Therefore, if we want to implement the EMFR SDS scenarios, there will be a huge need for new policy. Next slide, please. So here is a chart that shows in what sectors the reductions of climate forces will appear. The sectors that contribute the most are fuel production and distribution, the waste sector, and power and heating plants. And next slide, please. And here is a chart that shows the potential net benefits from the MFR SDS scenario for 4 different Arctic countries. As you can see, Russia has the largest net benefit potential, mostly because is still a lot of new technology not introduced in Russia, and therefore a lot of low-hanging fruits to pick. For US and Canada, there's a large potential benefits as well. And you can see that the US have a bigger potential than Canada. For Sweden, for Sweden, that is the largest Nordic country, the net benefit is not as large at all, mostly due to the size of the country, but also because a lot of technology is already introduced. Yes, so next, conclusions. So our conclusions are that the socio-economic effects for death, climate change, and investments in best available technology are all immense. The sum of the net socio-economic effects is positive for the MFR and SDS scenario for both year 2030 and 2050. But a large problem is that the net benefits will not affect the same actors as the costs. Yeah, so thank you for listening, and maybe there is time for some questions.